Upon completion of this module, students should be able to describe a PLC, discuss the components of a PLC and their respective functionalities, list the guidelines for PLC selection, describe the disadvantages of using a PLC, describe an MTU and an RTU and their functionalities, describe an HMI and a data historian, describe an industrial managed switch, a controller chassis, and a communication adapter. Describe a sensor and an actuator. Describe the desirable properties, sensors, and articulators. We made a cursory look at PLCs in the previous module. In this module, we will examine PLCs more closely. A programmable logic controller, PLC, is a self-contained computing device that is geared mostly for industrial control. It is programmed to realize the various functions required by industrial processes such as robot controls, equipment operations, status diagnostics, and so on. The PLC instruction set may include logic, timing, counting, communication, math, and I/O, input-output control. An Ethernet-enabled PLC is shown in the figure. The first PLC, introduced by Richard Morley of Bradford Associates in 1968, is known as the Modular Digital Controller, Modicon. It is designed to automate the functions of relay logic systems. Previous to its invention, relay systems tended to fail, which created a tedious troubleshooting process for technicians to find and fix the problematic relay. In essence, PLCs, which are robust devices and sturdy in harsh industrial environments, are used to address the issue of relay system failure that is frequently caused by overheating physical contacts. Further, the ease of customizing the functionality of a PLC through programming and its modularity makes it conducive to widespread deployment. Despite the proven merits of PLCs, they do have disadvantages. Unlike computers, they cannot handle complex computations due to a limited central processing unit, CPU, and a small working memory. In addition, it requires interface modules for communication and graphical display. The component diagram of a PLC is shown in the figure. Similar to a typical computer, a PLC has a central processing unit, CPU, which serves as the brain and is usually a 16 or 32-bit microprocessor augmented with a memory chip and other integrated circuits for control logic, monitoring, and communicating. The CPU controls the execution of instructions, communicates with other devices, and carries out logic and arithmetic operations, and performs internal diagnostics. The input and output I/O components carry out the analog and digital I/O operations. Due to the proliferation of PLCs in the market today, choosing a PLC can be a daunting task. Here's a non-exhaustive list of items to consider when choosing a PLC. Number 1, cost trade-off between performance and affordability. Number 2, processor capability, which refers to the PLC's ability to deliver expected functions. Number 3, storage capacity. The PLC must have adequate storage both in volatile as well as static memory. Number 4, power requirements. Power can be either DC or AC with different wattage. Number 5, connectivity protocol. This varies widely to several protocols such as Modbus, Ethernet/IP, Profibus, and DNP3, among others. Number 6, input-output capability and capacity. One must decide on how many I/O interfaces, AC or DC I/O ports, and capability of interfaces. Number 7, programming. The ease of programming and application development is paramount in deciding which PLC to use. And number 8, compatibility. The compatibility with other PLCs, devices, sensors, actuators, equipment, and working environment must also be considered. Obviously, PLCs operating in very well-maintained and well-conditioned buildings may not work well in very harsh industrial environments. Another type of hardware component for industrial control systems are the master terminal units, or MTUs, and the remote terminal units, or RTUs. A master terminal unit, MTU, is the primary controller in an industrial control system. It facilitates a two-way data communication and control of field devices. An MTU is composed of two basic components: a human-machine interface, HMI, and a communication controller. The HMI can be as simple as a single engineering workstation or as complex as a sophisticated operations center. A communication controller is made up of advanced network equipment such as routers and gateways, and programmable logic controllers that facilitate the ability to provide real-time processing of information and controls. The figure shows a master terminal unit, MTU, for a water distribution center. A remote terminal unit, RTU, is a field device that is equipped with wired or wireless radio communication interfaces. Its main purpose is to perform data collection and control functions for DCS and/or SCADA systems. A PLC in the field that is remotely accessible and manipulated via radio signals is also considered an RTU. Radio communication protocols may include 802.11 Wi-Fi, 802.16 broadband, 900 megahertz radio, and others. The RTU on the top right corner is controlled by a 900 megahertz radio transceiver. The RTU on the bottom right corner is controlled via cellular communication. The basic functions of a typical RTU include the following. Actuate. The RTU would set into motion the intended action by a field device, such as an actuator, a relay, or motor. Measure. The measurement function may involve process variables such as temperatures, pressure, volume, and so on. Collect. The RTU is used in the collection of data from field devices and equipment. Detect. The detection function of an RTU may coincide with the measurement function. For instance, in the monitoring of liquid levels, the level is constantly measured and monitored, which in turn triggers the detection of reaching the threshold value. In other instances, it can simply be a trigger mechanism built into the RTU to detect motion, vibration, smoke, or fire. Communication. Perhaps the most important function of an RTU is to communicate or transfer information to the MTU. This information may include, among others, measurement data, event logs, and equipment status. An RTU, being predominantly a field device, must be designed and built with the following indispensable properties. Ruggedness. An RTU must be able to withstand tough conditions and a harsh environment that are induced by man or nature. Flexibility. An RTU must be flexible enough to adapt to any communication protocol. Cost effectiveness. The cost of an RTU and its associated deployment must be justified by a reasonable return on investment, ROI. Secure transmission. Data transmitted by the RTU from the field must uphold the three tenets of information security: confidentiality, integrity, and availability. Sufficient storage. An RTU must have sufficient storage capability to be able to process data in cases of communication downtime and processing delay. Speed and robustness in communication. An RTU must be configured with a robust communication capability. In addition, a high communication speed is desirable for real-time processing. Low maintenance. Due to its remote location, an RTU must be built with very little need for periodic maintenance and field inspections. Data annotation. An RTU must be capable of data annotation or labeling in order for the main terminal unit, MTU, to properly distinguish each data item. Power resilience. An RTU must be supported by backup power to be able to remain in operating mode in cases of primary power failure. This can be accomplished by portable batteries or solar power. Next, we look at the HMI and data historian components of an ICS. An ICS is often furnished with an HMI to assist the operator to efficiently monitor and control the process activities and equipment. To supplement this function, the HMI provides visual, audio, and text alarms to initiate an alert on critical status of the system. The figure depicts a typical HMI. Another major component of an ICS is the data historian. The data historian, also known as process historian, is a database management system that stores information pertaining to system events, process variables, equipment statuses, environment variables, and other control information. The data historian configuration shown below depicts a factory talk historian SE architecture with the factory talk directory installed on the historian server computer. The data historian server in this configuration has the asset framework, analysis, directory, and data management services in one computer. Prominent usefulness of a data historian are found in the following areas. Process control. Control and monitor process variables such as speed, temperature, pressure, and flow. Production management. Managing production input and output levels, monitoring and operating costs, equipment capacity and utilization, quality control, and personnel efficiency. Safety and environmental monitoring. Monitoring of safety processes, alarms and critical events, failure rates, incident and response information, and environmental data. System security management. Managing system security events, monitoring data exfiltration, security data collection and analytics, and monitoring data network performance. Data historians are typically found in the following industrial and manufacturing applications: food and beverage industrial plants, power and utility generation centers, automobile manufacturing plants, plant and building energy management, batch and continuous manufacturing processes, and cloud data centers. A data historian may either be an in-house designed and implemented database system or a more robust commercial-grade database system built on top of an enterprise-grade database management system such as Microsoft SQL or Oracle database. A commercial off-the-shelf database server has a definite advantage over an in-house developed system. These advantages include, among others, the availability of a data acquisition interface with control system equipment and intelligent electronic devices, the robustness features of data redundance, transaction checkpoints, and other failover features, the capability of fast data collection and processing, the provision of an efficient data storage through compression, the built-in data security through encryption and access control mechanisms, and effective data query and retrieval. We will now shift our attention to switches and communication adapters in ICS. An industrial managed switch helps alleviate the burden of the ever-increasing demand for more connected devices on the Ethernet network infrastructure. An example of these managed switches is the Allen Bradley Stratix 5700. This switch is a compact, scalable Layer 2 managed switch with embedded Cisco technology for use in applications with small, isolated to complex networks. It is an industrial managed switch that is co-developed by Rockwell Automation and Cisco and facilitates the seamless integration of operations technology, OT, with information technology, IT, with tools and technology that are common to both. The convenient feature reduces configuration time and cost. A more advanced industrial managed switch, the Rockwell Automation Stratix 8000, is shown in the figure. This industrial Ethernet switch, built with Cisco technology, is a modular managed switch with a powerful feature set that provides secure integration with enterprise networking using tools familiar to IT professionals. It allows easy setup and diagnostics from within the Rockwell Automation integration architecture using tools familiar to manufacturing professionals. While the Stratix 8000 is a Layer 2 switch, the next in line switch, the Stratix 8300, is a Layer 3 switch that supports routing between subnets and VLANs. A Power over Ethernet (PoE) module, which can pass electrical power along with data on the Ethernet cabling, can be added to this switch. This allows a single cable to provide both data connection and electrical power to devices using such wireless access points, reducing wiring and improving the ability to turn devices on and off for power savings and added security. In order to accommodate diverse communication protocols, a chassis-based controller system is made available by manufacturers of control equipment. A notable chassis system is the Control-Logix system, which is manufactured by Allen Bradley. This system is shown on the figure, has the capability of handling multiple communication protocols such as Ethernet, IP, HART, DeviceNet, ControlNet, Data Highway Plus, Foundation Field Bus, and Ethernet. Further, it supports programming languages such as ladder logic, structured text, function blocks, and sequential functions. The Control-Logix Ethernet IP network enables a complete suite of control configuration and data collection services by layering the Common Industrial Protocol, CIP, over the transport network protocol tandems such as TCP/IP and UDP/IP. The Control-Logix Ethernet IP network enables a complete suite of control configuration and data collection services by layering the Common Industrial Protocol, CIP, over the transport network protocol tandems such as TCP/IP and UDP/IP. In addition, the Ethernet IP network provides the following features: HMI interaction and data tagging, message encapsulation with TCP/IP or UDP/IP, physical network connection with fiber or copper, compatibility with industrially managed switches, time synchronization, media redundancy, and application layer compatibility with control net and device net networks. The figure depicts multiple devices controlled on multiple networks. In this configuration, the control Logix chassis has 6 control modules. The device net module that controls a variable monitor power flex drive. The control net module controlling a flex distributed I/O. The Ethernet module that controls a distributed Ethernet ring network. An Ethernet module that enables HMI via a factory talk server. A HART module that controls flow meters. And a control Logix processor, 1756 L85E with 32 MB user memory. Another modular adapter chassis shown in the figure below is the SLC 500 modular controller system. The configured controller system consists of the chassis itself, power supply, CPU module, SLC 503, an input module, an output module, an analog input-output module, and a communication module running Distributed Network Protocol 3, DNP3. The processor module, SLC 503, in this system supports the following instruction set: bit, timer, comparison, basic math, move, copy, bit shift, sequencer, jump, subroutine, messaging, set and interrupt, FIFO and LIFO, proportional integration derivative, advanced math and trigonometric functions, indirect addressing, and floating point math. This module ends with an introduction to sensors and actuators. These are integral components of ICS. In a process control loop, the device that performs the measurement of a process variable and initiates an activation process is the sensor. The measurement can only be as effective as the sensor itself. The sensor effectiveness is based on the following characteristics. Response time. This property of the sensor describes its ability to respond to a change in the measured variable. This can vary depending on the type of the variable that is being measured. Pressure and temperature measurement might take a bit longer compared to a liquid level measurement. The response time property is very critical when the process control loop requires a fast response to changes in the measured variable. Accuracy. This property refers to the degree to which the result of the measurement made by the sensor conforms with the actual value of the control variable. Oftentimes, there is a tolerance value, which is the acceptable deviation from the actual value. As long as the measured value is within the tolerance value, the sensor is considered accurate. Consistency. The ability of the sensor in producing the same measured value given the same input parameters is called consistency. Sensitivity. This property refers to how well the sensor responds to the rate of change in the input value. A highly sensitive sensor should respond the same way, i.e., produce an accurate measurement in both low and high rate of change in the input value. There are various types of sensors, ranging from those that are mechanically driven to electrically activated. Limit switches are fundamentally physically driven devices that convert mechanical motion into electrical signals. A limit switch is shown in the figure. Proximity sensors are those that detect the presence of an object without the need for physical contact. A proximity switch is shown in the figure. Other types of sensors include Hall effect device, which detect the presence of a magnetic field, a photoelectric sensor that utilizes the light energy to detect the presence or absence of an object, and an ultrasonic sensor, which uses high-frequency sound waves to detect objects. An ultrasonic sensor is shown in the figure. Actuators are mechanical or electromechanical devices that provide controlled and sometimes limited movements in industrial control systems. The two basic motions of actuators are linear and rotary. Linear actuators, which work basically on a push or pull motion, are mainly used for positioning control. Rotary actuators, which function on a rotary motion, are used mainly in controlling flow valves. A linear actuator, a hydraulic type, is shown in the figure. There are 5 main types of actuators. Hydraulic. This type of actuator uses hydraulic energy for controlling motion. It relies on the principle of fluid compression to generate the necessary force. It typically consists of a hollow cylinder tube filled with fluid, a piston, and a rod. The drawback of this type of actuator is in its inability to produce an accelerated motion. Pneumatic. This type of actuator uses the energy of compressed air to produce linear or rotary motion. It is mostly used with a valve to quickly open or close a diaphragm to enable the start or stop of the fluid flow. Electric. In this type of actuator, electrical energy is converted to mechanical force to articulate a device or equipment. Typical applications for this use of actuators are opening and closing dampers, door controls, conveyors, and machine braking mechanisms. Thermal magnetic. This type of actuator can be controlled through the application of thermal or magnetic energy. It is much lighter and compact compared to the other types. Typical applications include PC board temperature actuators, remote switch control controllers, micro pumps, door locks, hair dryer cutoffs, and motor protectors. Mechanical. This type of actuator converts rotary motion into linear motion to produce movement. It consists of gears, pulleys, chains, rails, and other devices.